Welcome to the sixth portion of our unit on electric charge and electric field. In this part, we're going to be looking at calculations involving the electric force, or in other words, calculations involving Coulomb's law. Our first example is going to involve two charges. We're told we have a positive 4 Coulomb charge placed 2 meters to the right of a 5 Coulomb charge. So there's my positive 4, here's my positive 5, there's the 2 meters. I can look at this as a one-dimensional problem, so I'm going to let the positive x direction be to the right. Because opposites attract and likes repel, the force on the 4 Coulomb charge will be to the right, or in the positive x direction, and the force on the 5 Coulomb charge will be to the left, or the negative x direction. As we saw in the last part, multiplication is commutative, so all I have to do is calculate the magnitude for one of these, and I have the magnitude for both. So I'm going to choose to calculate the force on the 5 Coulomb charge first, because it's what's asked for first here in the problem. K is a constant with a value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. Q1, 4 coulombs, Q2 is 5 coulombs, and remember again, it doesn't matter which one is which, divided by 2 meters squared. And that works out to be 4.5 times 10 to the 10th newtons. I can now write down my two forces. So the force on the 5 Coulomb charge will have a magnitude of 4.5 times 10 to the 10th newtons in the negative x direction. And the force on the 4 Coulomb charge will have the same magnitude, but be in the positive x direction. For our second example, it's very, very closely related to the first one, but instead of having a positive 4 and a positive 5 Coulomb charge, in this case, I have a positive 4 and a negative 5 Coulomb charge. The setup, however, is exactly the same. I have 2 meters between my two charges. The 4 Coulomb charge is placed on the right. The negative 5 Coulomb charge, therefore, must be on the left. I'm going to define the positive x direction again to be to the right. Now I am dealing with opposite charges, therefore they are attracted. So the force on the negative 5 Coulomb charge will be to the right, or the positive x direction, whereas the force on the 4 Coulomb charge will be to the left in the negative x direction. I can find the magnitude of one of these. I guess in this case I'm going to do the 4 Coulomb charge. And I wanted a magnitude, so let's get rid of that arrow really quick. So that's going to be K, Q1, Q2 over R squared. So 9 times 10 to the 9th Newton meter squared per Coulomb squared. 4 coulombs, 5 coulombs. Notice I absolute valued the charge here. I don't want that negative sign coming in and messing things up. Just as with the last example, this math works out to be 4.5 times 10 to the 10th newtons. And now I can write my two forces down. F negative 5 on 4, or the force on the 4 Coulomb charge, will have a magnitude of 4.5 times 10 to the 10th newtons and will be in the negative x direction, whereas F4 comma negative 5, the force on the negative 5 Coulomb charge, will be 4.5 times 10 to the 10th newtons in the positive x direction. Now, those two weren't so bad. They weren't so bad. But part of that is because we're only dealing with 2 charges here. So what if there are more charges? What if we had 4 charges, for example? So here I have 4 charges distributed around a rectangle. I'm told in the problem that the sides of the rectangle have lengths of 0.5 meters and 1.5 meters. So I'm just going to write those in really quick. And what I want to know is, what is the force on the 4 coulomb charge up here in this corner? So I'm going to start by looking at the forces on the 4 coulomb charge, the directions of the forces on the 4 coulomb charge, due to each of the other 3 charges individually. And I'm going to think about opposites attract, likes repel. And the other thing I need is I need to establish a coordinate system. So I am going to use the standard coordinate system where positive x is going to be to the right and positive y will be upward. Okay. So let's start with the -2 coulomb charge. -2 and 4, that's a case of attraction. Therefore, this force will be in the negative x direction. Going around, I have a 3 coulomb charge. Those have the same sign, so it will be a case of repulsion. So it will go, oh, sorry, that was attraction that I just drew. A case of repulsion, therefore it's going to be up like this. And to give you a perspective, that is along the diagonal there between the 2 charges. The -1 coulomb and the 4 coulomb charge will be attracted. So the 4 coulomb charge will experience a downward force, or a negative y force, due to the -1 coulomb charge. Okay, so I've established what I expect the directions of these 3 forces to be in. The next thing I'm going to do is I'm going to calculate the magnitudes of these 3 forces. So I'm going to start with the -2 coulomb force first. So the magnitude of the attraction between the -2 coulomb charge and the 4 coulomb charge will be K times Q1, Q2 over R squared. So K was 9 times 10 to the 9th Newton meter squared per coulomb squared. One of our charges in this case is 2 coulombs. The other one is 4 coulombs. Remember, it's absolute valued. I don't want to deal with the minus signs here. I deal with those when I put the directions on. And the distance between the -2 coulomb charge and the 4 coulomb charge was 1.5 meters. When I multiply all of that together, it works out to be 3.2 times 10 to the 10 newtons, and based on the diagram that I had before, I know that this will be in the negative x direction, so I'm just going to make a little note there to remind myself of what that one is. Next, I'm going to work with the -1 coulomb charge and the attraction there. And you may be wondering, well, why not go around the outside of the square again? Well, the 3 coulomb charge is the hard one to work with, so I'm doing the easy ones first. Okay, same formula, KQ1, Q2 over R squared, but my values of K, or not K is a constant, of the 2 Q's and R in this case are not the same. So 9 times 10 to the 9th Newton meter squared per coulomb squared. Q1 in this case, I'm going to let be 1 coulomb, Q2 be 4 coulomb, and the distance between those two was 0.5 meters, which I have to square. And that works out to be 1.44 times 10 to the 11th newtons. And again, as a reminder to myself, I'm just going to put a little note here that that was downward. It's in the negative y direction. Okay, so now for the next one. The next one is the 3 coulomb charge. So I'm going to remind you really quick that we had a rectangle that was 1.5 meters on this side and 0.5 meters on that side. The distance between the 3 coulomb and the 4 coulomb is the diagonal of that rectangle, which I can find using Pythagorean theorem. So r squared is going to equal 0.5 meters squared plus 1.5 meters squared, which results in r squared equaling 2.5 meters squared. Now, you can take the square root here, and sometimes you need to take the square root here. But in this case, the number that's going to matter when we go to calculate with Coulomb's law is r squared. So we're just going to leave it. There's no sense in taking a square root and then squaring the result. The other thing I'm going to need to know is this angle, which I'm going to call theta. I can find theta using the tangent function. So tangent of theta will be the opposite side, which is 0.5 meters, divided by the adjacent, 1.5 meters, which results in an angle equaling 18.43 degrees. Okay, so I'm now in a position where I can figure out everything I need to figure out involving the force from the 3 coulomb charge on the 4 coulomb charge, F34. So pull in Coulomb's law again, K Q1 Q2 over r squared. Write down my constant, 9 times 10 to the 9th Newton meters squared per coulomb squared. 3 coulombs, 4 coulombs. My distance, r squared. Notice I have that up here, r squared. So this is 2.5 meters squared. And notice the square is just on the units. It's inside the parentheses. I've already done the squaring, so I don't need to square it again, which results in a value of 4.32 times 10 to the 10th newtons. But here's the problem. That's not along the x-axis, and it's not along the y-axis. Remember, this one goes up like this. I'm going to get rid of that little hiccup there with the writing. And this angle here is going to be that 18, I'm just going to call it theta again, but the 18.43 degrees. Which means I can now use trig to separate it into its components. So I have a triangle where this is going to be the x component. This will be the y component. This is theta, and the hypotenuse is F34. So F34x will be F34 cosine of, what was it, 18.43 degrees. And when we put the 4.32 times 10 to the 10 newtons in and multiply by the cosine of 18.43 degrees, you get this is 4.1 times 10 to the 10th newtons. I'll clean that up as well. Hold on. In the positive x direction. Remember, my coordinate system had x this way and y that way. F34y is on the side opposite, so I'm going to use a sine. And when you take 4.32 times 10 to the 10 newtons and multiply by the sine of 18.43 degrees, you get 1.37 times 10 to the 10th newtons. And as a little reminder again to me, that's going to be in positive y. Okay, so now I have all of my forces. I have all of their directions. I know what is going on with this problem as far as that. The last thing I need to do is find the net force by adding them all together. And of course, when I mean add, I mean we have to add them as vectors. So I need to find my net force. So F net x is going to be the sum of everything I have in the x direction. So I had F34 in the x direction, and I had F -24 also in the x direction. Remember, this guy, though, was in negative x. So when I put the magnitudes in, F34x was 4.1 times 10 to the 10 newtons. This one was in the negative x, so I'm going to subtract it off. Minus 3.2 times 10 to the 10 newtons. And that works out to be 9 times 10 to the 9th newtons. And because it turned out to be positive, I know that that is going to be in the positive x direction. F net y, similarly, will be F34y plus F -14. And as we saw earlier, F -14 is in the negative y, so when I put it in, I'm going to subtract it off. So 1.37 times 10 to the 10th newtons minus 1.44 times 10 to the 11th newtons, which works out to be negative 1.30 times 10 to the 11th newtons. That negative sign I'm now going to interpret and write this as 1.30 times 10 to the 11th newtons and make a little note to myself, hey, this guy's in the negative y direction. So there he is. Okay, so I now have the components of my net force in x and y. What I really want, however, is the magnitude and direction, so I have one more step to take. I have a triangle with F net x in the positive x direction, F net y in the negative y direction, so I drew it going down, F net along the diagonal, and I'm going to define this angle as phi. I can write that the tangent of phi will be F net y, opposite side, divide by F net x, the adjacent side, and when I plug my numbers in and take an inverse tangent, I find that phi is 86 degrees, which shouldn't really surprise me because my y component is so much bigger than my x component, almost a factor of 10 bigger. Okay. I can find the magnitude of F net using the Pythagorean theorem. And when you plug the numbers in, you get that F net is 1.3 times 10 to the 11th newtons, which seems like it's exactly like what F net y was, and really what's going on is round off error. We're not keeping enough digits to see a difference in F net from F net y because of the number of digits we're keeping track of here. And with that, I have completed this example. In the next section, we're going to move from this example. We're actually going to start with this example and use it to set the stage for calculations of the electric field.